this module. You will learn about conservation of momentum and the equilibrium of a particle. Let us observe the recoil of a gun when a bullet is fired. The gun and the bullet are in one system. Initially, the gun and the bullet are at rest, which means the momentum of the system is zero. As soon as the bullet is fired, it moves forward with a very high velocity. Thus, there is a force exerted by the gun on the bullet in the forward direction. According to Newton's third law of motion, the bullet too exerts an equal amount of force on the gun in the reverse direction, which is referred to as the recoil of the gun. If Fbg is the force exerted on the bullet by the gun and Fgb is the force exerted on the gun by the bullet, then Fbg is equal to minus Fgb. If delta t is the short amount of time for which Fbg acts, it is the same time during which Fgb acts. From Newton's second law of motion, the product of Fbg and delta t is the change in momentum delta Pb of the bullet. Similarly, the product minus Fgb delta t is equal to the change in momentum delta Pg of the gun. Initially, the gun and the bullet are at rest. Hence, their initial momenta Pig and Pib are zero. This indicates that the total momentum of the gun and the bullet as a system is zero. As the initial momentum of the gun and the bullet is zero, the change in momentum of the bullet and the gun is equal to their final momentum Pfg and Pfb respectively. Thus, the forward momentum of the bullet is numerically equal to the backward momentum of the gun, which is taken as negative. As the two momenta are numerically equal but opposite in sign, their algebraic sum is equal to zero. That is, the total momentum of the system is zero. We started with zero momentum of the system, and its final momentum is also zero. This shows that the total momentum of the system is conserved. That is, it remains unchanged. The law of conservation of momentum states that the total momentum of an isolated system of interacting particles is conserved. System here refers to a conglomeration of particles or bodies. For an isolated system, there are no external forces acting on it. Let us apply this law to the direct collision between two bodies. Let the initial momentum of A before collision be Pa, and the initial momentum of B before collision be Pb. When A and B collide, there are two forces created, one on each body, for the same interval of time delta t. Fab is the force on A by B, and Fba is the force on B by A. These two forces are equal in magnitude but opposite in direction. Now, the final momentum of A after collision is P-A, and the final momentum of B after collision is P-B. Applying Newton's second law of motion to the two bodies, we get Fab delta t is equal to P-A minus Pa, and Fba delta t is equal to P-B minus Pb. Applying Newton's third law of motion, we get Fba is equal to minus FAB. Substituting the values from equations 1 and 2 in equation 3 and resolving, we get PA plus PB is equal to P-A plus P-B. This shows that the total momentum before the collision is equal to the total momentum after the collision. This proves that the law of conservation of momentum holds true for all isolated systems. Now let us look at the equilibrium of a particle. When the net external force acting on a particle is zero, the particle is said to be in equilibrium. Applying the Newton's first law of motion to this situation, we can say that the particle is either at rest or in uniform motion. When the particle is at rest, we say that the particle is in static equilibrium. And when the body has uniform motion, we say that the particle is in dynamic equilibrium. Let us check out the equilibrium of a particle with multiple forces acting on it. When two forces act on a particle and keep it in equilibrium, then both forces must be equal in magnitude but opposite in direction. And the two forces must be collinear. That is, the line of action of the two forces must be same. Now let's consider a particle in equilibrium with three forces acting on it. Here, the three forces must be coplanar, that is, they should all lie in one plane. The resultant of any two forces is equal to, but opposite to, the third force. The third force, which is opposite in direction to the resultant and whose magnitude is equal to that of the resultant, is called the equilibrant force. The vector sum of the three forces must be equal to 0. When n number of forces act on a particle and keep it in equilibrium, the vector sum of the n forces must be equal to 0. The vector sum can also be determined making use of the three components of the forces. Sigma F is equal to 0. Sigma Fx is equal to 0. Sigma Fy is equal to 0. Sigma Fz is equal to 0. You have now reached the end of this module. In this module, you learned that the law of conservation of momentum states that the total momentum of an isolated system of interacting particles is conserved. System refers to a conglomeration of particles or bodies. For an isolated system, there are no external forces acting on the system. When the net external force acting on a particle is 0, the particle is said to be in equilibrium.